Good afternoon. Welcome to course Thermodynamics of Materials. We are into lecture 89 and 90 today. We are discussing excess functions, and we could not actually we finished this. We actually discussed and we went up to this point. But the problem is last 11 minutes, 11 or 12 minutes, this audio was missing. There was actually some problem that was our fault. Okay, so we should have been more careful. So today actually this type of problem will not arise because we have changed the microphone and also we actually changed the tripod stand. So everything is now good set. And I think today actually there won't be any problem in terms of audio or video. So let me go through this once more. Start with this excess function. Oh, by the way, before I start, I want to mention somewhere that one small point I missed in the last class about the diagram. Remember, phase diagram, the fourth one. What is this? That is phase diagrams. The phase diagram showing. So I am writing here. Phase diagram. Phase diagram showing intermediate phase, intermediate compound. The missed out point, missed out point. Last class. Just I will fill in today. Last class. Phase diagram showing intermediate compound. Intermediate compound. There actually strong negative deviation. The extreme, I am very sorry, extreme negative deviation in solid state and liquid solution still ideal, behaving ideally. What is the diagram like? This was all discussed. What is the diagram like? Quickly I am giving you. This is the diagram. This was discussed. So this is A, this is B, this is AB, this is AB, and the diagram was you may recall this. This I don't want to repeat this unnecessary. The point that I missed, the example for this diagram. Which system behave like this? Example. In all cases, the other cases, 4 cases, I have given the example. This one I forgot to give. Examples: calcium tin system. Another is calcium magnesium system, binary system. So this is the missed out point. Just before I start, I mentioned this. Now start actually excess functions. Okay, that we are functioning. Mixing functions completed. The excess function is what? This is GI bar excess. Start from this point. GI bar excess, which is known as partial molar excess free energy of I in real solution. Okay, you may write it at here today in real solution. In real solution. What is the excess? Excess about what? The excess is the difference. What is the difference? Gy bar real minus Gi bar ideal. How much it is excess above ideal? How much it is different from ideal? What is Gi bar? You know, partial molar free energy of I in the real solution. The solution under study. The solution under study is real solution. So Gi bar, so I may be A or B, and this is Gi bar ideal. Ideal, how can it be? If it is a real solution, how can it be ideal? Ideal, if the solution were ideal, then what is the Gi bar? So this difference will give you Gi bar excess, this difference. And what is the name of this? Partial molar excess free energy of I in real solution. In this solution, what is the value of excess? Because these are not same, so excess is this difference. So excess property are a measure of deviation from ideality. Here, okay. So now move on. Gi bar real, subtract Gi0 from both. So Gi bar real minus Gi0, and then minus Gi bar ideal minus Gi0. I have subtracted Gi0. So you please write here real, or I have written here. Gi bar real. Gi0 has no real or ideal because Gi0 is the pure state. This is not solution. This is not solution at all. This is a pure state, standard state. So I have subtracted this pure state free energy from either. If I do this, then what I get? This Gi bar minus Gi0 is known as RT ln AI. RT ln AI, and real. See, this is real solution for the real solution. And next is RT, same term, RT ln AI ideal. And incidentally, we know if activity of I in the ideal solution is nothing but the mole fraction. So mole fraction. So what is Gi bar excess then? RT ln AI over Xi. This is known as gamma I. This is RT ln gamma I. Call it equation 1. So Gi bar excess is RT ln gamma I, the basic equation. So two comments. It is no surprise that excess function should be connected to the activity coefficient gamma I. There is no surprise about it because both are a measure of deviation from ideality. Both are a measure of deviation from ideality. Second is, by the definition, this is the one first comment. Second, by the definition of excess function, this is the definition. Definition is here. What is excess function? This is the definition. Definition, you may write here. This is the definition. Definition of excess function. By the definition of excess function, the excess function for an ideal solution is what? We measure with respect to ideal. If the solution under study is ideal itself, so real becomes ideal and they become same and it is 0. It becomes 0. So for an ideal solution is 0 because ideal solution with respect to ideal, there is no question of deviation, and so result is 0. You can see here, okay. If this solution becomes ideal in real solution, if this ideal solution, then this will be ideal and these two terms is same. Obviously, no. There is no. So for ideal solution, there cannot be an excess function. This can be a good question to students. That what is the excess function? Say several excess functions are coming. So enthalpy excess, free energy, excess free energy, or excess enthalpy for an ideal solution. All excess for ideal solution by definition is 0. So these two. Next, excess is in short written as XS. So I have started. Delta G excess. Start. We'll use this heavily. Equation 1. Delta G excess. What is this? Again, you see, you can write delta G excess or short G excess. In short, I tell you why people sometimes drop this delta, because excess means a change. So then a delta means change. So it may be redundant. Forever actually it becomes clumsy or maybe space problem. So G for short description, GXS is what? This you have to follow. This is known as integral molar excess free energy. Like integral molar free energy of mixing, it is excess free energy. Integral molar should be divided into two partials, XA GA bar excess plus XB GB bar excess. This is actually, if it were delta GM, what you wrote, XA GA bar M plus XB GB bar M. No surprise, for excess similarly, this is the partial, these are the partial, two partial makes integral value. So XA GA bar excess already given here, RTLM gamma A plus XB times RT ln gamma B. So then what you get? RT in common, so XA ln gamma A plus XB ln gamma B. So box this and call it equation 2. Okay, this much we discussed last class, and audio was missed. Okay, for up to this point. So today we will move on from this point. So next we will consider this. So now what you will do? Sx, free energy known Sx. Now Sx is what? Tell me. Sx, or say it is actually a delta Sx. This is nothing but or delta Sx. If you know delta Gx or Gxs, how will you get Sx? Gx is known, Sx or Gxs is known. How will you get Sxs? Standard procedure, standard. Free energy entropy, from free energy entropy by derivative of free energy with respect to temperature, with pressure and composition fixed. So do write this minus with negative sign. Recall, you have to, often you will use this, often. Delta G or Gxs, since I am writing short, Gxs, Gxs under pressure composition constant. Recall this, okay? If you have forgotten, you should not. This is the last time maybe I am showing you how. This is dg is starting to source equation. Source equation is what? Beginning is dg is dp minus s dt. Okay, what is s from this? This is good for which type of system? Fixed mass, fixed composition. Example, 1 mole of an ideal gas, 3 moles of iron. So fixed. I am repeating though this, okay, in case you forget, or okay, fixed mass, fixed composition system. For this, from which you get S is what? Minus del G del T at constant pressure. At constant pressure it drops. So my constant pressure, and this is fixed mass, fixed composition, so equals right composition. Okay, so this is. So from this you get this, S is minus del G del T at composition, okay, del T pressure and composition for this. So this is written. Now follow. if you write, see, follow this. This is the root source equation. Source equation. If you write SXS, see, SXS, then it will be GXS. If you write it is delta S, it will be D delta G. Just in place of G delta G as it is here, delta S. If you write here delta S 0, standard state, then it will be delta G 0. You have already used this. Now delta SM, this will be delta GM. Now it is see delta S XS, or in short SXS, it will be GXS as it is written here. See clearly? So always this, So I have written this. Now you have to differentiate. Which equation? This one. You differentiate this. See this is, there are two terms follow, which is temperature dependent here. T is temperature dependent. X is the composition fixed, is a constant. X is constant, but gamma is a temperature dependent term. And the temperature dependence of gamma is our next topic, next discussion. So we have to be careful that there is a temperature dependent term here. So you do this. First you consider that there is a negative sign. So minus R, I consider this part XA ln gamma A plus XB ln gamma B. This is very easy differentiation. Very easy first year. Okay, differentiation. Okay. So this is first term. Here I consider temperature is the variable and this is constant. Next I will do what? I consider temperature as the constant and this is the variable. So next is temperature being constant minus RT. Continue minus RT. What? Tell me. XA cannot be a variable. Constant. Gamma is a temperature dependent. So write that del T ln gamma A, and as you should write in bracket pressure composition. Then what is the first? This is first term, second term likewise plus XP del, right here, del XB del ln gamma B by del T constant pressure composition, and give a third bracket outside, third bracket. This is your equation 2. Actually I should box this. Should I box this important information. Call it equation what? 3. Next is what? 3 things out. GXS, SXS. Then what? Enthalpy. HXS. HXS is very easy. When 2 are known, remember when 2 are known, third is easy. From G is H minus TS. So follow this. If G is known, then how to get S? Just take derivative, temperature derivative. Keeping pressure composition constant. And then how will you get the third derivative enthalpy? How? Just by G is H minus TS or H is G plus TS. That I will do. GXS, HXS is what? Right? GXS plus T is XS. XS. Okay, what is this? If you do this, you see okay. If you do this, what is the TSXS? Follow this. If you multiply by T, these two terms, TSXS, this is the SXS. So multiply by T, this term minus RT XL and gamma A plus XBL and gamma B is exactly this term. Is a GXS. So this term and T times this term with negative sign cancel out. The remaining T times of this second term here. So that write this out is minus RT square times just this term XA del ln gamma A by del T pressure composition since actually I have to write this. I do one thing. This equation 3 I am writing slightly up here. This is equation 3. This one equation 2. This is 3. Now this will be 4. Plus what? Tell me. Read this. Copy this. XB B ln gamma B by del T. Sorry. Del T pressure and composition, and give a third bracket outside. This is our expression for H excess or delta H excess. Okay, so this will be again, if you put a box maybe. Then this will be our equation number 4. So repeat quickly. First get the definition of GI bar excess, partial molar excess energy. What is this about? It is about the partial molar energy of a real solution less partial molar energy of the solution of the ideal solution, considering if the real solution were ideal, where it is not ideal if it were. So this is actually the, so how much the real free energy, partial molar free energy is, how much above the ideal free energy, how much it is excess above ideal. The difference, simply difference. So this is the real minus ideal. So excess function are a measure of deviation from ideality. So this part we did. Then we get RTL and gamma. It is interesting. All excess functions should have gamma. The activity coefficient. All. See, for example, here see gamma. Here gamma. You cannot escape gamma in excess function. Why? Again, it is no surprise that excess function should be connected to the activity coefficient gamma, because both are a measure of deviation from ideality. See, and this is actually no surprise, because both actually measure both are a measure of deviation from ideality. Okay, say. And next is by the definition of excess function. Excess means how much it is deviated from ideal solution. But if the solution itself is ideal, there is no question of any excess function. So by the definition of excess function, the excess function for an ideal solution is 0. So this is, next is delta Gx. We have found 3, 1. This is okay. This is the integral value. These are the partial molar free energy. So shall I write here? I have written. So I am writing here also for you. What is the name for this? Oh, I have written. Sorry. At the beginning it is written. So it is partial excess free energy of A. You don't have to write in real solution all the time. Partial molar excess free energy of A. This is partial molar excess free energy of B. Together known as, this partial against integral. Together is known as integral molar excess free energy. Once delta G, remember, free energy is known as a expression for free energy is known, entropy is damn easy. How? This is this is the clue. This is the source equation. Take temperature derivative of the free energy function to get the corresponding entropy function. Here it is excess from the Gx. So Gxs, take the derivative with negative sign. Careful. Once done, then third easiest is G plus Ts. G is H minus Ts. You can note this, G is H minus Ts, from which or H is G plus Ts. You have already done number of times these things. Okay, so this actually. So so this part is okay. This part is over. Okay, see this. So and what is the value? This value is this. Okay. So excess function. Excess function. Okay, excess function discussion is over. But we'll take up okay the next topic. What is that? That is the gamma is a temperature dependent term. So variation of gamma, the activity coefficient with respect to temperature. This is the next one. So let me remove this. This is no more excess functions, okay, but this will be coming subsequently. So this is next topic is variation of excuse me. Excuse me for a minute. Hello. Your mother close the door. Noise is coming. Well, tell her that this is required. No. This is required means because the noise is coming here. बोले बुझी दे. Sorry for the interruption. So next is what? Variation of next topic. Variation of activity coefficient gamma I with respect to temperature. Variation of with temperature. This is the next topic. But it is all under solution thermodynamics. Okay, see, I start with the Gibbs-Helmholtz equation. I believe you remember well Gibbs-Helmholtz equation. I am writing for Gi bar m. See, we follow it, then you will d Gi bar m. Gi bar m means delta Gi bar m. Okay, name means mixing means change. Delta is there. You may drop this, no problem. By T by del T, del 1 by T. Again the same deal. Pressure composition is known as what? Hi bar. This is Gibbs-Helmholtz equation or Gibbs-Helmholtz type equation. What is the original Gibbs-Helmholtz? Recall. When I say recall means it is already discussed at length. So what is this recall? Tell me original. If you ask me, I will write this d G by T del G by T del 1 by T under constant pressure composition is known as HI bar. H, okay, see, H, okay. Alternatively, this is Gibbs mode. Alternatively, this is important also equally. Alternatively, what is del G by T by del T, constant pressure, constant composition as before, is nothing but minus H by T square. Alternative. Why this? Note del 1 by T is what? This is differential. Is minus 1 by T square del T. This you know. Okay, so you have used this, manipulated this way. So now you follow same principle. You follow this. G you have considered. Now if you write GI bar, says I am giving you everything here. See how many ways you can write these thermodynamic functions. If it is G, H. If it is GI, HI. It is GI bar, HI bar. If it is delta G, it is delta H. Nothing else. All are remaining same. For example, delta G by T, del 1 by T under constant pressure, constant composition is delta H. So just change here as required, then corresponding change there. Delta G, delta H. You write here again, see, continue. Delta G 0, what it will be? Delta H 0. In fact, you have studied this before. The name is Van 't Hoff equation. So delta G 0, delta H 0. Again now, see, mixing functions. G, delta Gm, then it will be delta Hm. You write Gi bar m, it will be Hi bar m. Now excess function. Gi bar excess, Hi bar excess. Whatever you write here, so we have done this. See here, G I have replaced by Gi bar m. So I will get on the right hand side not H but Hi bar. Oh, I am very sorry. I am very sorry. What mistake I made? Tell me. It is Gi bar m. G is Gi bar m. H will be Hi bar. I am very sorry. I am very sorry indeed. So this is the Gibbs element. Now we will move on with this. Gi bar m is what? Tell me. Or our job is to find the temperature dependence of activity coefficient. Or del Gi bar m is what? You know, R T ln Ai by T by del 1 by T, you know, is Hi bar m. Partial molar enthalpy of mixing. So now this T cancel easily. So what you get? Keep on writing. Or the R, actually R is a constant. I will take the other side. But before this, what is ln Ai? Tell me, what is ln Ai? Ln Ai is Ai is what? Ai is what? Gamma I times xi. So put this ln gamma I. Since it's a log, multiplication is plus ln gamma I plus ln xi d of this by over del 1 by 3. 1 by 3 is, and give this, oh I am very sorry, I have missed this other line, that is this third bracket closer, pressure composition, the constant is what? Pressure composition, again write, is Hi bar m. Okay. Or what? Tell me. Del ln gamma I, give a bracket, del 1 by T pressure composition is what? Right. Oh, I have made a mistake here. See, R I have shifted to the right hand side. R R was there, so you have to write R this side. Hi bar M by R. Or you write this Hi bar M by R. This is kind of activity coefficient temperature relationship common by Hi bar M. Okay, this, let me remove this part all over. Actually I have no point retaining them anymore. This is about excess functions all over. Good, very good, very good. Alternatively you can write, alternatively tell me, follow this, alternatively, follow the logic. This is alternative. This is del 1 by t, this is del t. And what you will get, it is not h alone anymore. It is h by t square with negative sign, following this rule. Okay, note is okay. This is your differential calculus. So alternatively, what you can write? I am writing in follow del ln gamma I. Call it, since I am not giving any equation, I will give this as one equation. Is what? Equation 2 and equation 1. Yes, sir. Equation 1 and then the equation 2 are coming. Ln gamma I. No, del 1 by t I will not write, rather just del t. Then what change I have to make is Hi bar M, but t square will be there, so it will be RT square and negative sign. So this is another one. Call this equation to alternative form. How gamma changes with temperature. Again, oh sorry, I missed which point. Careful. Pressure. We often in thermodynamics we don't give much attention to the constraints. Constraints are very useful and give you full concept. So I actually tell you, in passing, I tell you in passing something different, very different. That in passing, I tell you the three. This is my opinion, purely my own opinion. Yeah, I have not actually borrowed from anyone, any author, or anyone else. There are three things. This is from my experience with thermodynamics. Three things have made thermodynamics difficult for the students, or maybe other professionals, okay, or thermodynamic professionals. In passing note, three things have made thermodynamics difficult. Thermodynamic study a difficult subject. For students, okay, maybe others also. What are the three things? This is my opinion, my own opinion. What is this? Number one, just D. D has actually cannot handle D. Mixed up with D, delta, and many other things. That I'll explain. D, this term D, differential D. This is actually has caused much difficulty. Second, reversible. The term reversible. Third, equilibrium. The term equilibrium. These three things, according to me, is responsible for making the subject very difficult, and many students turn away from the subject. Follow me. dy, what is this? I tell you, I give an example. I'm writing one thing. G is H minus Ts. So dg is what? Oh well. Even earlier one. Okay, this is also equally even easier one. H is U plus Pv. Okay, no problem. What is dH? du plus P dV. Tell me, plus bdP. Now see how delta H is written is okay, correct. Delta H is written P delta V. All D is replaced by delta V delta V. Is it possible? I have seen in some textbooks. Delta H is delta U plus. This is always wrong. It cannot be possible. For example, if it is a constant pressure process, then this term will drop. Okay, constant pressure process, this will be out. Then you can write. This is right. But here you cannot. You have to see integration. So here you are integrating under constant pressure. This is integration constant pressure, and next time you are into constant volume. Okay, and pressure is varying. If pressure is constant, here pressure will drop. This term will drop. So it is okay. Wrong. This D also, and also okay, many cases. For example, I am giving this. This second reversible is what? Confusion with reversible process. Okay. Confusion reversible with equilibrium. There is a subtle difference. Subtle, very fine. Reversible is a process and equilibrium is a state. But reversible process move through equilibrium states. This is actually, there is a subtle difference between these two. For example, if you consider, if you say ds is ds, I'm writing ds greater than ds is okay. Or reversible with reversible process with equilibriums. Reversible with okay, fine. Okay. What is this value here? ds is okay. We consider this ds is
আগামী 21 ও 22 মার্চ 2025 শুক্রবার ও শনিবার
this is equilibrium.
প্রাঙ্গণে শিলিগুড়ি সাই বাবার
This versus
ও সন্ধ্যা আরতি অনুষ্ঠিত হয়েছে।
this versus
উপলক্ষে সমস্ত সন্তুষ্ট অধিবাসী বৃন্দকে উক্ত অনুষ্ঠানে
ds is 0. So see, at equilibrium ds is 0 is what? ds, any change from this will be either this way or that way negative. ts, what is ds? What's the application of ds here? ds is refers to equilibrium is 0. ds is 0. This is for equilibrium, actually for equilibrium or reversible process. Interchangeably used. So ds equilibrium is reversible is 0. So say if this ds, any small change from this equilibrium state is a point. Any change, how can it be 0? It is dropping, declining. This way also. This is also negative. So what is this? How will you use this ds? This is I discussed you ds. This actually ds is Here it is actually ds by, suppose here NB, NC, I am very sorry, 3C, N, ds by dn is 0. This is nothing but delta S is 0. Now, what is this? Delta S is 0. Is what? Now, no state, single state. Equilibrium state delta is 0 means S product is S reactant. Or S product minus S reactant is 0. Right? This delta S is 0. This is the meaning of this. So, how subtle this thing is. So, this is the reaction A plus T. So, S of 3SC SC minus SA plus 2SB. Sorry. Anyway, this you know with G you discuss. But when it is applicable, when entropy will be used as a criterion, what type of system it is? Isolated system. Right here somewhere, isolated system. Means delta S is 0. So it is a constant internal energy, constant volume system. I always also add, okay. Anyway, constant internal and no non-mechanical work. Okay, so this point. This is the difference. This is the important thing. Now we will say D. I am talking of D. D also reversible also. D and reversible will go together. Reversible also definition: infinitesimally small driving force making the system pass through equilibrium states. So reversible means equilibrium, that is confusing for the reversible. So that is there. So now ds is 0 for reversible. How? ds is 0 for how? This is equilibrium state, but reversible means I will move on. Reversible process takes from one state to another. Any finite change, anything, as much as irreversible process can do. So ds will be 0 for reversible. A change, and you can see, you might say change. What is the change? Anytime any change you see, it's tending to be negative. Keeping under the equilibrium condition, if this process is this equilibrium condition, under equilibrium condition, this maintained. So if you can carry out this reaction under equilibrium condition, that can be done. Okay, equilibrium condition, reversible process I taught you. Evaporation. I taught you reversible process, evaporation. In fact, evaporation you can consider instead of this big reaction, evaporation. Liquid to vapor, evaporation. Okay, since I have started, actually it will be too much. But this may be another example I take you. Okay, so how it will be 0 for reversible process? Because they always remain under this equilibrium condition when delta S is 0. This composition are such, the state is such that delta S, this difference is 0. So any movement from product and reactant under this condition doesn't make any change in entropy of the system, because product and reactant, they are actually at par, same, but changes. A reactant converts into product, no problem, because under the same composition should not be changed. Okay, this is actually under reversible condition you have to. I am giving better example. This is a follow this easier example. Liquid vapor. Say a liquid and a vapor. Temperature T. So water may be better. Water, since this example I took. Temperature H2O. Here you will understand how to carry out reversible process. A chemical, I tell you what, since this is a chemical reaction, it can be carried out in the same manner as that is through infinitesimally small driving force. That this I will easily show here. Or another is what you can electrochemical cell. they are using non-mechanical work, involving non-mechanical work, and actually by making the driving force E, okay, D E for electromotive force, D is this. But here you follow this, that is for two ways of carrying out chemical reaction reversibly. One is just infinitesimal change, so that is it start from the equilibrium condition and then infinitesimal change, and the system will move on. For example, here what? Suppose P is 1 atmosphere. Sorry. Let me clarify this point. Sorry, actually. Let me erase this. So, pressure is 1 atmosphere. You know very well what is the temperature here. I am very sorry. Coming to this. Temperature is, I told you, 69 degrees centigrade. That example I am taking, 342 Kelvin. Water vapor pressure is how much? 0.3 atmosphere. 0.3 atmosphere. So this inside pressure, what is the vapor pressure? pH2O. Yeah, this point. This is vapor. You have vapor. The liquid. This is liquid vapor in equilibrium at this temperature, at this pressure. This is the equilibrium. Now reversibly you carry out, this equilibrium will not be upset, but process will go on. The whole liquid will be converted into vapor reversibly, as much as irreversibly. Irreversibly can convert whole liquid into vapor or part of this. Reversible can do the same thing, but reversible will maintain this. So how it maintains? Infinitesimally driving force. It is not that driving force is zero. Infinitesimally small is the key word for reversible. That is subtle. That eludes many minds. That is infinitesimally small driving force. Equilibrium, but not 100% equilibrium. Then if it is equilibrium, it is no process anymore. Reversible process is a process under equilibrium. So what is this? How will carry out this? 0.3 reverse to make it reversibly. I am writing here. I am writing here 0.3 minus dp, where dp tends to 0, tends to 0 but not 0. So then there is actually imbalance of pressure. Inside is this I will not discuss today. This is 0.3, this is 0.3 minus dp, imbalance. So this will expand. Low pressure will expand so that it becomes 0.3 minus dp. Then temperature requires strictly 0.3. So then some liquid will be evaporated. Small though, but this way you move. You could repeat, whole liquid will be evaporated into which so. Irreversible is what? This is reversible approach. What is reversible approach? 0.3 minus delta. Yes, any value. 0.1, 0.2, 0.3, 0.4. I'm sorry. 0.1, 0.2, 0.25, etc. Even 0.3 itself. But this is dp. dp tends to 0. Right? dp cannot be compromised. dp tends to 0. Don't say any value. Okay. This I discussed. So this is actually where reversible and equilibrium process. So if you carry out this way, now I tell you, I take it this was the reversible process. What is the delta G for this process? Suppose you remove 1 mole H2O. Sorry, let me write nicely. Process 1 mole H2O liquid goes to 1 mole H2O vapor. 1 mole H2O liquid, you are producing vapor. There may be some vapor, but extra vapor. 1 mole liquid convert this. What is the process? Process is let me write. Vaporization. H2O liquid goes to H2O vapor. So 1 mole you want to convert fully into 1 mole H2O vapor. Note, at 342 Kelvin, and 0.3 atmosphere. You know, this is your, remember this diagram, liquid vapor diagram, recall, phase diagram, liquid vapor diagram. This is your 342 Kelvin, this temperature, and this is how much value? 0.3 atmosphere. This is, I told you, the pressure can be vapor pressure, vapor pressure as well as the external pressure for liquid vapor. This is the liquid. Recall this. So this point actually, this state, this is this, and now on this point we want to carry out a reversible process, and finite change will be, infinitesimal will be small driving force, but change will be finite. How? Magic. So this is what, why this happens? What is the delta G? Tell me, delta G is how much for this process reversibly? Shall I write here? Reversibly. What is the delta G? Delta G is, tell me, see at this, see this is the equilibrium point. What is the meaning of this? Molar free energy of liquid and molar free energy of vapor same. So system is losing here. System is losing some liquid and gaining vapor, but they have the same value. So the loss and gain same. So no change. So delta G is 0. That is the criterion for reversible process and equilibrium. Delta G is 0. Equilibrium is a state. If you consider a process like this, this is actually chemical reaction process. This can be done. If you consider another reaction easier than this, N plus O2 is MO2, simple because oxygen is there. So here that reaction can be carried out actually with external pressure is PO2 equilibrium at that temperature. And then that pressure point, suppose that pressure is 0.003 minus dP. Or rather minus dP, rather minus dP MO2 will dissociate, or plus dP rather, then N plus O2 will go to MO2. In the equilibrium manner it will move. That actually covers both the confusion, reversible and equilibrium. So this is about reversibility. So delta G, this is why recall this is the criterion for equilibrium. And less than 0 for spontaneity, and I say also irreversibility for this, and this is reversible as well as equilibrium, because under equilibrium they are moving. Under equilibrium, what is the character? G of this, G same. Under this condition, G of, let me write, G of H2O liquid is G of H2O vapor, and this is, that's why this is equilibrium diagram. At this condition, they coexist. Enough is enough. So this equilibrium is also one thing I tell you about equilibrium confusion. Equilibrium actually, this actually there is some confusion with respect to reversible process itself, equilibrium, and there are other confusion about equilibrium. Actually, I think one great thing is that many students don't know, or say they respond when they are asked what is the equilibrium state. They say when the forward reaction rate is backward reaction rate. Okay. So this is A plus 2B is 3C. Forward reaction rate is backward reaction rate. That is the definition of equilibrium state at that state. But this is a kinetic definition. They are studying thermodynamics. They have to say when the free energy of the system will be minimum, or alternatively at, there are three alternative statements. G prime PT will be minimum, or say delta G is 0. Simply delta G is 0. The free energy of the system will be minimum. Okay, for all possible composition, at a certain composition it will be minimum. His free energy. Other composition will be greater. So that is the equilibrium. Or simply say delta G is 0. These are thermodynamic statements, but they are using kinetics. Thermodynamics has nothing to do with the kinetics. Thermodynamics does not use any time. Second, nothing, nowhere in this we are not considering time. Kinetics is about time, speed. Thank you. I could have given more example. Equilibrium you will see actually later on. You will see this. Okay. say, about equilibrium. Since actually I have already, I will start this equilibrium. One thing I tell you. See, I said this difficulty. When you Illingham diagram, you are considering two systems. See, equilibrium, listen, maybe equilibrium confusion. I will remove all this. Then I will only start from this point. Equilibrium confusion. There are many, but one I am actually does now remember equilibrium confusion. But one is already a given reversible equilibrium. Equilibrium, and also a very bad way of talking of equilibrium is that forward reaction rate is equals backward reaction rate. What is this? This is a kinetic statement. Kinetics is a different subject, and thermodynamics is an independent subject. Kinetics depends on thermodynamics because rate equation is that is the equilibrium constant there. Thermodynamics does not depend. So anyway, equilibrium confusion. I am giving the Illingham reference, Illingham diagram. How difficult sometimes confusion. See, thermodynamics is a subject. You cannot memorize. You should not memorize. You should not try to memorize. All you can derive yourself. Equilibrium confusion reference Illingham diagram. See, this is say AaO2. This is BBO. This is the delta G0 is the plot you know. This is the 0 perhaps 0, and this is positive, increasing, and this is the temperature. So you consider this temperature called T1. This I discussed, but I am just highlighting this the equilibrium how difficult it is. So suppose this is at this point the reaction PO2 equilibrium for what system AaO2 is 0.03, and what is this? At the same temperature T1, point 0.04 atmosphere. PO2 what? System BBO. Sorry, PO2 BBO. So repeat this, At this temperature name T1, say 500 Kelvin, say 1000 Kelvin. So what is happening here? PO2, how will you get this? From what? Delta G0 is minus, delta G0 is minus RT ln K. K is what? The reaction is what? A plus O2 is AO2. So delta G0 is minus RT ln K. It can be easily shown. Delta G0 is RT ln PO2. So delta G0 greater means PO2 will be greater for a given temperature. We are discussing at a given temperature T1. So PO2 of this gentleman, this point is 0.04, which is the BBO system, for BBO system. 0.0. How the reaction moves on? You have taken all four. AaO2, BBO pure, solid. At what temperature? T1 in a closed system. Constant volume system. Constant volume, not constant pressure. Constant volume, constant temperature, T1 system. So what happens? How the reaction move on? So, and filled with oxygen 1 atmosphere. Shall I get some space? Oxygen, AO2, oxygen 1 atmosphere, but constant volume. So how the reaction starts? At a start. What is the oxygen? I will quickly say 0.03 atmosphere. Since my point is equilibrium. First is you have to get what is the equilibrium. Yeah, you are not given here anything. Just get this. What is the equilibrium value? This is the actual value of 1 atmosphere. So equilibrium value, you will simply take the delta G0 either from your data book or from this figure and use delta G0 is minus RT and PU. So PU2, and if suppose you found this value as what value? PU2 value for this system, for the AAO2, this is written here, this temperature 0.03 atmosphere. You know? And similarly calculated this for BBO, which is slightly greater because delta G0 increases. You clearly see delta G0 increases, PO2 increases. No wonder. And this delta G0 is greater, positive this way. This is negative this way. 0 is here. These are all negative values. So positive. 0 you can write here. Equal 1, positive. 0. So you have no difficulty. This is positive side, this is negative. Don't worry. Increasing. Very good, very good. So now, under this condition, 1 atmosphere, A, suppose you start with A, say. You can start with B also. A will do what? You see, what is the equilibrium value? Equilibrium value is what? Now, 0.03 atmosphere. So, and the actual value is 1 atmosphere greater. Q less than K, so reaction will occur. So, obviously, A will move forward. I have to give some little bit introduction, otherwise I cannot get to the point I want to elaborate, I want to highlight. A to A2 will occur. Then what it will do? This is greater than this, Q less than K, reaction will occur, then what will do? Yes, let it occur. Then it will keep on reacting, oxidizing until the pressure drops to the equilibrium value of it. See, concept of equilibrium coming. What is the equilibrium value? It brings down the equilibrium to its equilibrium value of 0.3 atmosphere. Once this started, then what happens to B? B's equilibrium value is 0.04 atmosphere. See, B's equilibrium value, these are PO2, shall I write here? PO2 equilibrium. You understand this? PO2 equilibrium. You write the PO2 equilibrium. One is equilibrium, another is giving pressure, actual pressure. So, but anyway, this reacts and down, oxygen reacts down, forming AO2. You suppose for the timing there is enough of A. Okay. So anyway, this is point. Then what does B do? This I discussed. I am repeating. B is not satisfied. B's equilibrium value is 0.04. It is not satisfied with 0.3. Why I am writing 0.3? This value 0.03. Sorry, 0.03. It is not satisfied. It wants to reach 0.04 in the system. No. So actually 1 atmosphere has been converted to, if I may write this way, 0.03. Then it says, no, I am not happy. B is not happy. B is happy with 0.04 only. So it will try to change the partial pressure of oxygen to this value 0.04 so that it will be in equilibrium. So this how it will do this 0.04? What is the procedure? You write this B plus O2, you write somewhere 2B plus O2 is 2BO. How will you increase the pressure? Dissociation of BO. So the oxygen is generated. So the 2BO will be moving to B, other direction. So what it will result? When it will give up or relent and stop, when it is satisfied. Equilibrium is the satisfaction always of all reaction. For all reaction, equilibrium is the satisfaction point. When the reaction stops. So equilibrium. So what value for this? 0.04. So how? Which way? Obviously not this way. This oxygen will be even lower, but it want to increase to 0.04. So this way. So PO2 is 0.04. If I may write here in this diagram, it is nice. Now no more 0.04. And the moment 0.04, again A is actually in difficulty. A2 system is not in equilibrium because its equilibrium requirement is 0.04. So why now you don't know I will reduce this. So what will happen next time? A will further react and produce PO2 is 0.02 and 2BO2B. I don't have space here. It will be 2BO2B. Means this is repeated. This is repeated actually. 2BO2B. BO2 is, sorry, I am very sorry. So I write somewhere this line. I'm writing somewhere here, where, here. I will remove all this. This line 2BO then moves towards BO dissociates, like this line of repeating. B plus, you will give a direction. 2B plus O2. 2B plus O2. What pressure it will try to, it will establish its equilibrium value 0.04. 0.04. So actually again you see this can be 0.04, 0.03. You can cancel, keep on doing. So as a result, since to give the complete story, what I taught you. See A moving in the AO2 and BO in the B. So what is the direction of the reaction? A move to this AO2 and 2BO. This is the spontaneous direction. AO2 plus 2B. And for which delta G in this all our center state is negative and spontaneous. And reaction keep on occurring. Okay. So there are many other questions which are the final phases, etc. equilibrium. My question is, see why my question is, it is 0.03. See first, A reacts with AO2 and reacts down oxygen to from 1 to 0.03 atmosphere. This is also atmosphere. Then see follow this. The why equilibrium is confusing. Follow this. So this is equilibrium, no confusion. First of all, you have to find that it is the equilibrium. This is the equilibrium value. This was the actual value, that is, and Q less than K. Its equilibrium is 0.03. Actual 1. So Q less than K. So delta T was negative. That's why reaction occurred. This is not, we have no difficulty perhaps. And stops when equilibrium is reached. And B was actually now B will not take up. BO again dissociate into this. For BO, this is my question. Remember, BO, for BO, what is this? BO is what? BO is what? What is? We actually often say Q less than K. Q less than K means this is the actual quotient, this is the equilibrium constant. So now you follow 0.03 is the equilibrium value for AO2 and 0.04 is BBO equilibrium value. So its equilibrium is this, but it is subjected to a system. Okay, consider this. It is subjected to a system which is 0.03. B says when this step is attained 0.03, suppose for the time you remove this 0.03, now B says 0.03 atmosphere. For B it is actual. Now why this happens? For B this value 0.03 atmosphere, B's equilibrium value is what? That cannot be changed, 0.04. What is this? It must be Q versus K. Or say PO2 equilibrium versus PO2 actual, if I am right. PO2 actual, Q less than K, PO2 actual versus PO2 equilibrium. What is the BO2 actual? I'm telling you. BO2 equilibrium for B, follow the reaction. Why BO when dissociates, that is the more difficult point about the equilibrium. Student starts remembering why. Starts memorizing why. This you have to tell them this is not the, this is the equilibrium value 0.04, but to it the 0.03 value is the actual, as if acting as the actual. So now you must have actual and equilibrium. Then you can decide the reaction will occur or not, or which direction. So Q and K. Okay. So or say actual versus PO2 equilibrium. That will also do. So it says equilibrium is 0.04, but actual is 0.03. Actual at this state when it says then says no, there is a class and I am not be satisfied, I will make it 0.04 dissociating due to BO into B in the moving in this direction. So what is the confusion? So you might argue that sir, this is the equilibrium for BBO and this value appears to BBO as an actual value, but it is actually an equilibrium value for AO2. So what is equilibrium value for one becomes the actual for the other. This is the confusion sometimes maybe. So always actual versus equilibrium other is initially follow initially why the reaction takes place. Why? Because actual is 1. Starting value 1 atmosphere written. 1 atmosphere written. Closed system 1 atmosphere oxygen. And the 4 solids are given. So actual and equilibrium is 0.03. So since actual is greater, so the reaction takes place very easily in this direction. Anyone can many Q less than K, okay, or say delta G is negative, okay, or in terms of Q, see K is nothing but PO2 equilibrium. So write PO2 equilibrium, PO2 actual comparison. So this time, so PO2 equilibrium. This is equilibrium, but what is the actual here? This is another equilibrium. No, that is the actual. For as far as BO concerned, it is the actual. Similarly for AO2, this is its equilibrium. But if it produces maintains in the second case, if it maintains 0.04, it will be treated as the actual for AO2. Equilibrium is equilibrium value. That is equilibrium value is actually kind of okay from delta G to theoretical value. That is already decided value. And what it is subjected to, what pressure of oxygen, that is actual. Starting also I think this is easy. So this is equilibrium, then this. Similarly next step, this will, when this reaction will consider what is around it, say 0.04, then you treat 0.04 as the actual, but which is the equilibrium for this. This is the equilibrium actual. Confusion maybe there. Thank you very much. See, these are the things. If you are alert, then there is no difficulty. Then if you also, it should be alert. So can I remove this? A lot of in passing, okay? Maybe little bit clumsy, but just these are actually some I wanted to. Okay, I wanted to point out to you that these are the difficulties of thermodynamics. Okay, thank you. Understanding, sometimes understanding is difficult for these reasons. Thank you very much. So this is equation 2. Remove all this, all. Let us get to this. Now this is these two equations I have obtained. Okay. Now, now you tell me what is this? Okay. So consider 3 possible situations. Before this. So see this equation. So can we say Hi bar m is a measure of temperature dependence of gamma I? It's very bad. Hi bar m decides how much dependence of gamma I with respect to 1 by T means T. Yes, that's so. We note Hi bar m. It is better both from both you will get this. Here also, the same. Here also see gamma I versus temperature. This decides. So equations 1 and 2 state that state that what it states? State that HI bar M, remember HI bar M partial. Bar means partial, right? And the name is there. Okay? I, A or B. How much time? Roughly?
30 minutes.
Oh, thank you. State HI bar M. So bar means partial. Means partial. When it's the integral, you don't have actually say there is no bar. Okay. See, anyway, you have seen this. Okay, very good, very good. Like delta HM, delta SN, delta GM, integral. So partial molar enthalpy of mixing. I have written many times. The HI bar M is a measure of the temperature dependence of gamma I. And here I am explaining further. Consider three situations. Dependence of gamma I. Okay. Gamma I means activity coefficient, right? Activity coefficient. Oh, HI bar M. So shall I write here? It is what? It is what I am writing here. Partial molar enthalpy or mixing of I means I means A or B. Measure of temperature difference or activity coefficient. Sorry. Activity coefficient. Let us go slowly. What is this? Gamma I. Okay. This is one comment we make, and this is right. So, to explain further, consider three possible situations. One. What is this? See, consider HI bar M is consider positive. HI bar M is positive. What is this? You know, it is a positive deviation system. Okay, showing positive deviations. Solution right. Solution showing positive deviation. Showing positive deviation from ideality. That is HI bar M is positive and what? Gamma I in that case greater than 1. Okay. Now what you see from this? Now tell me, if HI bar M is positive, equation 1. From equation 1. And use equation 1 right here. And use equation 1. But this will be easier. Equation 1. Follow. This is positive. What is the significance of this? This leads to what? As this is positive. Now this plot slope is positive. Oh, yeah. This is positive means this R is positive. So this slope will be positive means what is this? When 1 by T decreases, the positive, if decreases, gamma I decreases. And then gamma I means gamma I decreases. Or, right? Or T increases, gamma I decreases. This is the message. This is a message for positive deviation. If you increase the temperature, gamma I will decrease. So I will give a figure for this on the top later. But complete this. Second, solution showing negative deviation. What is this? HI bar, right underneath. HI bar, M is negative and gamma I is less than 1. Recall this, I discussed it. So when this happens, tell me, when 1 by t decreases, what happens? Follow this equation from 1. Remember, use equation 1. Use equation 1. So follow. 1 by t decreases. So this is negative, remember this time. Negative means, so if the slope negative, if this decreases, this increases. 1 by t decreases, gamma I increases. 1 by t decreases, gamma I increases. Or in terms of t increases, this increases, this decreases. Okay? Gamma I increases. These two equal. Third I will write here. What is the third? This is positive deviation, this is negative deviation. No deviation. No deviation. What is the name of this? Ideal solution. Raoult's law, etc. And HI bar M is how much? Enthalpy of mixing. Ideal solution last time, number of things are 0. 0. See, positive, negative, 0. Very systematic. And gamma I is how much? For ideal solution is 1. So very easy. Greater than 1, less than 1, equal to 1. What is your comment? See this and make a comment. This is 0. So what is the temperature dependence of gamma I? Independent. Gamma I is independent of 1 by t or t, because it is 0. So gamma I is not going to be changed by temperature, is not function of temperature. This is the three things discussed. But I will give you figure for these two, maybe 3. So let me remove this quickly. These are not required. This is all over. These are all over. We will draw this figure. So positive deviation first. Positive deviation system binary. As you write, I will often write this. X moves from 0 to 1, means this is pure A, this is pure B. You know, this side is what? What you write? Activity of B. Because Raoult's law plot. Raoult's law plot, how you plot this? Because it is a activity B is XB. Okay, better this way, better maybe. Better. So activity of B. Oh, I cannot draw well. So this is activity of B is XP equation, ideal solution, Raoult's law, etc. Not ideal. Positive deviation. I start this. This is positive deviation I am showing. What is this? Tell me. How will show this? Suppose I am showing this a large positive deviation. 1. Next, 1 temperature. Say it is actually T1 temperature. Next, I change the temperature. T2, increasing. As I increase, deviation is slightly less. T2. Okay. So let me draw another one. This is our third temperature. Even less. I am closing towards the Raoult's law. Ideal solution. So this is T1, this is T2. In case you have difficulty, T3, T2. And note that T3 greater than, I write here, T3 greater than T2 greater than T1. So temperature is increasing in this direction. Temperature increasing. So T1, T2, T3 greater. What happens to this? As a result of which, now to understand this, you tell me what is happening. To understand this, you have to consider a given composition. So you will better understand. Because remember, why I tell you, this is some composition, XP. Certain composition XP say, 0.2 say, 0.2 say, just does not matter, XP. Why? You are studying where? Gamma and temperature. What is the gamma? The activity and temperature. So for a given, how you get gamma from activity? Gamma is right somewhere. Gamma B is always AB activity over XB. That is the, and when AB is XB, gamma B is 1, for example, ideal solution. That is ideal solution. So gamma B is this. So if you want to correlate this diagram in terms of activity coefficient rather than activity, to find activity and how with temperature this activity coefficient, activity coefficient, find activity coefficient from the activity values and then see how these activity coefficients are changing with increasing temperature, means this way. So let us see, since this is a fixed XB, so you see this is the activity at the T1 temperature, this is the, this is the activity. Shall I use different color? We need to work. I do not know if it will work. So see, this is at this composition, this is the activity. This is the activity. Top one, the middle one, this is the activity, and the lowest one, this is the activity. So this is the activity. For a given composition, if activity decreases, you see, activity decreases for a given composition. Activity decreases, gamma B decreases. So gamma B, we see gamma B decreases as temperature increasing, and that is the character of positive deviation. Gamma B decreases as temperature increasing. So we see, we can comment here. The good pen, good, helpful. Okay, thank you. So comment. So with temperature increasing, gamma B, which is gamma B, what is this? Gamma B, always you see, oh by the way, what is the gamma B? Gamma B is activity by mole fraction. So see, this mole fraction, and what is the, at this mole fraction, what is the activity that is equal to mole fraction? The Raoult line. So here the mole fraction activity mole fraction. So any value greater than these are greater than the mole fraction, means gamma is greater than 1. So no surprise that gamma is greater than 1 and this is a positive deviation. I repeat, for this activity composition, which activity is equal to the composition? The one that falls on the line ideal solution. What is this line? Oh, sorry. Actually, this is the line. AB is XP. So here this mole fraction, this activity same. So any greater activity means same. So you have a higher activities means gammas are greater than 1, still greater. So greater than 1. So in general, so it increases. So gamma B, the right second. So it is better actually. What way I gamma B decreases. Tell me, toward, is it falling toward ideal solution line, Raoult's law, toward moving towards x means gamma b is 1, okay, toward 1. As t increases, gamma b decreases toward 1. 1 means this line. A b is x b is gamma b is 1 here. This line. So clear? Okay, repeat. So few things I told you here. Gamma b's are greater than 1. Very easy. Where gamma b is 1? Gamma b is 1 for this composition at this point. So any point above this, any activity above this are actually here gamma b, AB by XB. Same composition activity is increasing, gamma b are increasing. Becoming more than 1 means greater than 1 means positive deviation, as I know, gamma b greater than 1. Now this gamma b is highest here. Gamma b decreases towards 1. Now the temperature effect. If we increase the temperature for this given composition, gamma b is gradually decreases towards 1. And similarly, what will happen? This is positive deviation system. And you write gamma b, so write here gamma b greater than 1. So negative deviation, I am drawing this. Similarly, I hope this will be better. Again write xb moves from binary system. I am always considering 0 to 1 unless mentioned otherwise, okay, and it is activity b. So again you see reference is ideal solution. Good, very good. This time activity b is xb, right? Ideal solution, write this like this, ideal solution. And you can note also, okay, very good, very good. Then negative deviation is what? This way. The maximum negative I consider. Then with increasing temperature, actually sorry, bad. I have actually another one to draw, so not so like this. Third is what? So what is this step? This is again T1, T2, T3. Right here again, right here, T1, T3, right? T3 is greater than T2, greater than T1. Happy? Okay, again, so write this way as temperature increasing, write this temperature increasing from T1 to T2 to T3. What happens? What is the gamma? Again, apply the same trick. Consider a certain composition xb is 0.2, say. Now you have the opposite thing, obviously. So it is 0.2. This is the activity is xb. So here activity is, okay, 0.2. So if first of all you see for a given same composition, if activity from this point, what is the activity? Means this. Gamma b activity fixed. If activity decreases, increases, gamma b increases. Follow. Activity from this point to this point increases. See, read this. Point. This is 1 point. There are 3 points. This is 1. So you see activity for these 3 points, activity value increases for given composition means gamma b increases. So as you move from this curve to this curve to this curve, like from T1 to T2 to T3, as you increase the temperature, gamma b increases. So what you will write in the same manner as T increases here, what you will write? As T increases, gamma b, what happens here? Gradually increasing. See, because for same composition activity is increasing, gamma b increases. What you write? Towards what? Towards this line, the ideal solution line. It is below this. gradually moving towards the ideal, towards increases toward 1. So this is a negative deviation. I have written here. Positive deviation system I have written here. This is a negative deviation system. I should write here negative deviation system. And gamma is what here? Gamma B is less than 1. So less than 1, gradually as you increase the temperature, increasing towards more, and as you increase temperature, it will more and more increase toward 1. Okay, so this is the increasing. So as temperature increasing, you can see why gamma is less than 1 according to this figure. Quickly, 1 second, you can very easily follow this. This line is what? Activity is mole fraction. This line, top line, activity is mole fraction. So if this 0.2 here, what is this value? This value 0.2. This value 0.2. So below this value, activity smaller than this. So this line is smaller than this, activity coefficient will be what? If activity are below this, activity decreases, same gamma B decreases from 1. So gamma B is maximum is 1 here in this case. All other activity coefficients, activity coefficient is activity divided by mole fraction. So for the same mole fraction, if activity decreases, so gamma also decreases. And moreover, you decreases. And why it is less than 1? See, this is the point. If I may draw this, this is not green. This is the point. This is the point. This corresponds to activity gamma is, see, this line is activity B is XB. Activity of B is XB means gamma B is 1. So this point is gamma is 1. Now activity decreases, gamma B decreases. So it is 1. So the ones which lie below, where activity is smaller than this activity, then that will be less than 1. Okay, progressively it is less and less and less than 1. Okay, so in fact all activities here, activity coefficients are less than 1. I should repeat this. Okay, clarify this point. So first of all, think this: for a given composition, see here activity increases. For a given composition, activity increases for this with these 3 curves. And for given composition, activity increases, gamma B increases. Gamma B increases how? As we increase the temperature T1 to T2. This curve T1, this curve T2, this T3. So as T increases, gamma B increases toward obviously 1. And these are already less than 1. I have written here gamma B less than 1. These are gamma B greater than 1. Gamma B, all gamma B less than 1. Why it is less than 1? Quickly, this is important also. This point means what? Activity of B is mole fraction. So activity. So what is the activity value? So this is the activity value. This is reference activity B. And what is the, okay? Now below this point, activities are less. So below activity, this point, what is the activity? At this point, I draw another line. This is the activity B is XB. So here activity of B is XB means 0.2 and gamma is 1. So now as activity B decreases with the same composition means gamma decreases. So all values are less than 1. Here all values are more than 1, greater than 1. And what happens? What is the role of temperature? As temperature increases, then this actually gradually, what happens? Gradually increases here, it will move to greater than 1, that will continuously decrease and decrease in the direction of ideal solution. Here it is less than 1, it will increase towards ideal solution, that is gamma is 1. So that line. So one thing before I leave today, what is this? Again I repeat, pressure composition. Fortunately this line is there. This I will explain again and again. What is this? Pressure composition. It is not, I forgot to write. I said 3, no? 3 I said. 3 I said. The 3 things. Please correct this. not three, four. Three things make make thermo difficult. I am very sorry. According to my opinion, Martin, these are not three things, not four things. What is the fourth? I missed out. Fourth is what? Constraint. In thermodynamics, the constant we tend to omit. Constraints. So what are the four things that make thermodynamics difficult? Constant. For students, what is this? First is just D, differential D. And okay. That differential D, okay. Second is what? The concept of reversible process. Third is equilibrium. Fourth is constant. Use of see every time constants. So how many times I am writing constant? Okay. DG a moment ago, DG constant pressure, constant temperature, many. So you should not avoid. So here, what is the application? What is the real life use? This is what you determine gamma I. Idea, follow this. You have taken a system AB, right? 30% B, 70% A. Say 30% manganese, 70% iron. And you have determined gamma of manganese. Say is iron, B is manganese. So gamma at that composition fixed. Then what you are measuring gamma. Activity coefficient experimental can be done. This I am not discussing. So gamma, okay. Pressure composition fixed. So you measure this.
3 minutes. 3 minutes.
Okay. Pressure, temperature. Okay. See what I said. You carry out the experiment. Okay. See, I tell you what. This. Very good. You measure this. Okay. Keeping each time actually you will measure pressure, composition, temperature fixed. Say. Pressure composition fixed. And temperature, first temperature is T1. Okay, that is constant. Okay, well. Pressure composition fixed, then you measure this gamma for one temperature, first one temperature T1. During this measurement, temperature T1 is remaining T1. That is also constant. Pressure composition also constant. That is already there. Pressure is say 1 atmosphere, 2 atmosphere. Composition is say 70%, 30%. So temperature is T1, you carry out this run. How will you carry out that? I am not taking up for you first clarify this thing. So this temperature, you carry out an experiment, okay? You measure activity coefficient. Activity actually there are processes by which you can determine activity. Equilibrium constant process by activity and composition you will gamma. Okay. So T1 temperature. Next run is not T1, T2. Again find gamma. Pressure composition previous value means 1 atmosphere or 2 atmosphere or whatever, 1 atmosphere say, and composition 70-30, and find this new gamma. And third is again change the temperature, again carry out this experiment for this T2, the whole experiment under this T2 and pressure composition. Next T3, change T3, pressure composition fixed. So what you see, actually you get a number of gamma S and number of temperature and get this value there. These are the other one, d1 by t, okay? And plot this, plot. Again gamma I versus d1 by t maybe or dt. Then you will get this better is d I will suggest del 1 by t, then it will be simply hi bar n by r. Suppose it is straight line.
Less than 1 minute.
Then the slope will be what? If you follow this, I will remove this, it is hi bar n by r. Del 1 by t is plus hi bar n by r. So supposing that it is straight line, then the slope is hi bar n by r. So this is the significance, and you can determine hi bar enthalpy of mixing, partial enthalpy of mixing, provided you know the number. You follow this, okay? So thank you very much. Oh, one thing still remaining. I'm sorry, I forgot that, but that I will cover next class. Okay, starting from this point, next class, and that I will complete. Then I will take up partial molar free energy to integral free energy, integral molar free energy, integral molar free energy to partial molar free energy. Next class, and finish something about this. Okay. Thank you very much. With these words, okay, I thank you very much for your cooperation, for your patience, for your attention, and for your interest, etc., etc. So today we are actually call it a day and see you next class. Okay, bye.